In our previous session, we modeled the transition of an abstract mathematical space as it settled into a stable, persistent structure. The core conclusion of episode 11 was that gravity does not need to be inserted as an external force. Within general emergence mechanics, it operates strictly as a depth gradient in persistent space. By combining local phase structure with the rules of global admissibility, we established a direct mapping where gravitational behavior is indistinguishable from the underlying geometry itself. Translating gravity into geometry forces a necessary theoretical confrontation. We have to look closely at the equations we use to describe that very geometry. Standard gravitational laws rely entirely on physical constants, specific numerical parameters like big G, that dictate the precise scale and magnitude of the physical effects. We have to ask if it is logically consistent to treat gravity as a geometric output while continuing to treat the mathematical constants governing it as immune to that same geometric logic. If persistence geometry is the root system generating these laws, we must interrogate it to see if it also generates the constants tuning those laws. In standard physics, on the left, constants are primitive givens, external parameters floating above equations with no origin. Contrast this with general emergence mechanics on the right. Here, everything originates from one root node, persistence geometry, branching downward equally to laws and emergent constants. Theoretical depth increases when a framework sources its governing parameters from the same structural geometry used to describe the system's behavior. The unification ambition of GEM relies entirely on this pivot. Physical constants must transition from being unexplained mathematical inputs to inevitable structural consequences of the vacuum. To make this transition, we first observe how chaos organizes into measurable stability. In the context of GEM, emergent is strictly defined. We are separating it completely from ideas of randomness, arbitrary assignment, or spontaneous generation. High energy states effectively mask these parameters. Emergent constants only become measurable when the geometry cools and establishes a baseline of long-term persistence. Therefore, we define emergence strictly as a stable, low-energy geometric summary of a much deeper, highly complex underlying structure. Here is the core mathematical reframing principle required. Constants must now be read algebraically as either a structural ratio or a response coefficient. We term these effective coefficients closure parameters. Within an admissible vacuum, they provide the necessary boundary limits that allow persistence geometry to function without spiraling into failure modes. By redefining fundamental to mean stable at low energies, rather than primitive and unexplainable, the framework removes the philosophical block against analyzing constants geometrically. We apply this reframing to the big four constants. Starting in the first quadrant, we have the speed of light, c. In this framework, c functions as a fundamental transport limit. Structurally, it is the limiting ratio between spatial stiffness and temporal response within the admissible vacuum. Moving to the second quadrant, we examine the gravitational constant, big G. GEM defines G as a specific metric of depth coupling rather than an arbitrary multiplier for an attractive force. Structurally, G is the scale that connects the organization of matter to its corresponding depth gradient response in persistent space. In the third quadrant, we have Planck's constant, h bar. This serves as the action quantum. It is the absolute minimum action scale, defining the precise phase transport granularity required for the vacuum to maintain structure. Finally, in the fourth quadrant, we evaluate Boltzmann's constant, Kb. Structurally, Kb operates as the informational bridge, connecting the raw data of persistence geometry directly to thermal excitation. Through the lens of GEM, the specific numerical values measured in the lab are merely low-energy shadows cast by these four distinct structural ratios. We must draw a strict boundary here between legitimate geometric derivation and numerological pattern matching. We are not attempting to reverse engineer arbitrary fractions to arrive at known values, like exactly 3 times 10 to the 8th. The intellectual focus here is changing the theoretical classification of what kind of thing a constant is, entirely independent of its observed numerical value. Deriving these structural ratios directly from persistence geometry requires strict mathematical discipline and rigid algebraic constraints. Requiring constants to exist as explicit geometric ratios serves as an internal safeguard. It prevents theorists from simply inserting magic numbers to fix equations when a model breaks down, a common flaw in past approaches. A valid constant must now survive a rigorous derivation from first principles. It cannot rely solely on empirical observation for its theoretical justification. Constants are no longer exempt from structural justification. Demanding this level of rigor is exactly what separates foundational mechanics from mere curve fitting. It is equally important to define the exact boundaries of the GEM unification program as it stands today. This session is focused exclusively on the philosophical and structural reinterpretation of constants. We are making no claims of having fully derived the exact final numerical values of these constants at this stage. Theoretical physics has a long history of claiming premature victory when the final, exhaustive mathematical derivations are still missing. We will avoid that error. However, laying this structural groundwork, shifting the perspective from unexplained inputs to geometric outputs, is a mandatory prerequisite before any future mathematical proofs can even be attempted. Scientific progression regularly requires reframing the question entirely before you can solve the equation. Recognizing constants as emergent properties is that necessary first reframing. The primary arc of our course so far points in a single direction. Just as gravity was successfully reread as a depth gradient, physical constants must logically be reread as structural limits. This marks a total shift in the definition of fundamental, moving our foundation away from primitive, unexplainable inputs and grounding it entirely in stable, emergent outputs, which leaves us with a question to ponder. If the constants are emergent, then are we measuring nature's deepest inputs, or just the stable, low-energy summary of a more primitive geometry? It is highly probable that our most precise physical measurements are merely skimming the stable, low-energy surface of a much more complex persistence geometry operating beneath them. In Episode 13, we will step back to view the full macro shape of general emergence mechanics and confront what still remains unresolved in the framework. A theoretical framework reaches its maximum depth when constants emerge as inevitable geometric consequences rather than arbitrary inputs.